Hey guys, so in this video we will be talking about electrons and quantum numbers. And really the point of this video is to show you where we are going. This is the stuff that's really applicable to chemistry, and you may have learned a lot of this in a chemistry course where you talked about a little bit of quantum chemistry. And this is really where quantum mechanics can be very, very useful, especially in the field of chemistry. There's a ton of uses. But this is really one of the main ones of how electrons behave in atoms and how you can describe the electron orbitals in atoms. And so in this video I want to sort of show you, hopefully you may have seen this before, but I want to show you where we are going and the things that quantum mechanics will tell us. And in fact, everything that I talk about in this video, eventually by section 7, we will have proved by the end of section 7. And we will really have derived this using the laws of quantum mechanics. Perfect. So the first thing, right, is we talked about Bohr's model, where you have the nucleus in the center of the atom and you have the electrons orbiting around it. And as we talked about, that is not true. In fact, in the quantum mechanical model, what you have is you've got a probability cloud. So a probability cloud of where you are likely to find the electron. And in fact, it doesn't have to be shaped like a circle around the nucleus. It could be shaped like this. And we'll talk about that in this video, what the shapes are, and we'll eventually, as I said, we'll show these shapes, and we'll actually mathematically show how we know what these shapes are, which is very cool. So we're in a probability cloud, and the probability cloud is called an orbital. That is the probability cloud an electron is in. And it is described by certain quantum numbers. So that is really what our focus of this video will be. So we'll talk about some different quantum numbers, and I've got a table set up here, right, with the name, the symbol, the possible values of the quantum number. That's what I mean by possibility. You'll see when I put numbers on there. And then how it's related to the orbital and what that quantum number will represent. Okay, and I couldn't really think of a better term for this, but maybe you can as you're watching this. You'll see what I'm sort of talking about. Okay, so the first is the principal quantum number. The principal quantum number. It has the symbol n, lowercase n. It is an integer, so its possibilities. It can be an integer, and it can go from the 1, 2, on and on to infinity. There's no highest value. The highest value we know of in the ground state, in the lowest energy level of an atom, is 7, but that doesn't mean it can't go beyond that. Okay, how is it related to orbital? It represents the size of the orbital. So the size of this probability cloud will be really represented by this n. If you have a larger n, the cloud will be larger compared to the smaller n values. And it represents we call it the shell, or also known as the energy level. The shell or the energy level. That's the principal quantum number. The next quantum number is the azimuthal quantum number. And it is represented by the symbol L. And it also must be an integer. But it can go from 0 all the way up to n minus 1. So the highest value it can be is n minus 1. So for example, if n were 3, L could be 0, 1, or 2. If n were 7, it could be 0, 1, 2, 3, 4, 5, or 6. If n is 1, it can only be 0. Okay. The next thing is its relation to the orbital. L represents the shape of the orbital. So in fact, right, the main difference between this orbital and this orbital, right, is their shape. So these orbitals will have different L values. In fact, this one will have L equals 0. This one would have L equals 1, and we'll talk about that in a minute. The next is the next quantum number that we can talk about is the magnetic the magnetic quantum number, and it has the symbol m sub L. And this can also only be an integer, but it can be negative. It can go all the way from negative L, it can be 0, up to L. So for example, if n is 2, right, L could be 0 or 1. If L is 1, then ML could be negative 1, 0, or 1. If L is 3, for some n value, if L is 3, M could be negative 3, negative 2, negative 1, 0, 1, 2, or 3. So there would be 7 possibilities. So on and on. Hopefully that makes sense. The relation to the orbital, the magnetic quantum number, represents the orientation. The orientation of the orbital. Okay, and I skipped this for the last one. The azimuthal quantum number, this represents the subshell. And we'll talk about that. The next thing I just want to point out is that these two quantum numbers, n and L, these both correspond to the energy. So even though n is the energy level, both n and L describe the energy of the orbital. Okay, so the energy of the orbital is determined by both n and L, not determined by ml. And ml is the last quantum number that describes the orbital. So we're going to kind of break this off here. Pick a new color. Okay, so we are bringing this off here. These represent the orbital. Okay, we have one more quantum number that does not actually represent an orbital at all, and we'll talk about that. So our last quantum number, which I'll put here in blue, is the magnetic spin quantum number, and the symbol is m sub s. Now this only has two possibilities. It can either be positive 1 or positive 1/2 or negative 1/2. Sorry. So positive or negative 1/2. Those are the only two possibilities for the magnetic spin quantum number. And it is not related to the orbital. Okay, so now that we have this straight, we've talked about all of our quantum numbers. Let's look at sort of what they represent. And we'll talk about really what are these shells and what are these subshells. So I'm going to erase this up here. Okay, so let's look at the different types of subshells, really is what we'll be talking about here. And the first thing is an alternative naming system that we have for the values of L. So we have, for different values of L, right, we have L equals 0. So I'm going to erase this and I'm going to put that there. L equals 0. So for L equals 0, we're going to call this S. And L equals 1, we're going to call this P. L equals 2, we're going to call this D. L equals 3 will be F. Okay, so L equals 3 is F, and then we actually can go on. L equals 4 would be G, and then they just continue alphabetically, although I believe they skip J. Okay, so now let's look at the different possibilities of L for different possibilities of N. So we'll make a little chart here. Let's use that color here. Okay, so this is our value of n. And so n will have 1, 2, 3, 4, 5, and it goes on. And then we'll have different possibilities for L. So L could be 0, 1, 2, 3. We'll stop there. So actually the highest possibility we'll have up to n equals 4, and then we'll do this for up to L equals 3. Okay, so now we have a naming system for the subshells. Okay, so these are the shells. This is the first shell, second shell, third shell, fourth shell, or first energy level, second energy level, third energy level, fourth energy level. And now we can look at the subshells. And so remember, L equals 0 is S. And so the subshell that corresponds to L equals 0 and n equals 1, right? So we'll look at n equals 1. The subshell that corresponds there is going to be called 1S. Okay, 1 because of the n value, S because of the L value. Okay, now for n equals 2, we could have then 2S, but then at n equals 2, L could also equal 1, right? So we can have 2S or we can have 2P. So this is just a naming system for how we name the different subshells of an atom, which correspond to the n and L. Okay, for n equals 3, we could have L equals 0, 1, or 2. So we could have 3S, 3P, or we could have 3D. And for n equals 4, we could have 4S, 4P, 4D, or 4F. Right? And then we could go on for other values of n. So these are the possible subshells for each value of n, and then for each value of L, right? Because the subshell is represented by n and L. And each of these subshells, the reason why they're so important is each subshell will have a different energy, right? Because it's a combination of n and L, which is the energy. Okay, so now we can look at the number of orbitals, right? Because each value of ml corresponds to an orbital. So now we want to look at how many orbitals are allowed in each subshell. Okay, and so we'll sort of just do this manually, and then we'll kind of find an equation for this. Okay, so for L equals 0, we can have m equal to 0, right? So there's only one value of ml. So I just want to look here at the number of ml that we can have. And so for 0, we can only have 1 ml. So any s orbital can only have, or any s subshell can only have 1 orbital. Okay, now what about p? Well, if we have L equals to 1, then ml can be -1, 0, or 1. So we have 3 possibilities here. 3 possible orbitals. So this is the number of orbitals in red here. For L equals 2, right, there are then 5 different possibilities for ml. We could have -2, -1, 0, 1, or 2. So there are 5 different orbitals in L equals 2. Okay, so what this is saying is there's one 1s orbital, one 2s orbital, one 3s, one 4s, right? Any s orbital, there's only one. There are 3 orbitals in the 2p subshell. There are 3 orbitals in the 3p subshell, right? The number of orbitals only depends on the letter. There are 5 orbitals in a 3d or a 4d subshell, and then there are 7 orbitals in a 4f or a 4g, or however more, or not 4g, it would be 4f or 5f or 6f. In an f subshell, there are 7 allowed orbitals. Okay, so this just sort of tells you how many orbitals are allowed in a certain how many orbitals are allowed in a certain subshell. And you can use the formula that the number of ml in a certain orbital is equal to 2l plus 1. So now the last thing we can talk about is what is called the Pauli exclusion principle. Okay, the Pauli exclusion principle. And what that says is that no two electrons in an atom can have the same set of quantum numbers. Now there are 4 quantum numbers here. We have N, L, ML, and MS. This is where magnetic spin comes into play. There are 4 quantum numbers, and no 2 electrons in an atom can have the same set of these 4 quantum numbers, right? So for an orbital is described by N, L, and ML. Well, then the only quantum number left is MS, and there are 2 possible values. So that would tell us that there are only allowed to be 2 electrons per orbital. Okay, so this is the Pauli exclusion principle. Exclusion. Right? No 2 electrons can have the same set of quantum numbers, but what this really means is there's only 2 electrons per orbital. Right? And that's where the name exclusion comes from, because there's no other electrons that are allowed. So we're excluding electrons from an orbital once we have 2. We only have 2 electrons there. And so what that would mean is we can have we can look at the number of electrons allowed in a subshell. And we'll talk about that in a minute, but the first thing I want to get to, I'll just keep this, so we'll keep the Pauli exclusion principle in the back of our head, is I want to look at, well, we talked about the size and the shape, but what exactly are these? So I've got a diagram up here. Okay? And this shows the different subshells. These are the shapes of the subshells. So this is the S subshell, it's just a sphere. Then the P sort of looks like dumbbells. The D looks like a clover, and then you have this one in the middle. And now, as you can see, these are different values of M. So this is so for any N, and then the N's would just make it look bigger or smaller, right? So that's just what N does. But in terms of the shape and orientation, this is L equals 0, ML equals 0. Okay, this whole thing is L equals 1. This is the p orbitals, but so we've got ML equals -1, ML equals 0, ML equals 1. And then this is L equals 2. And so we've got for ML, and I'll just put it a little bit here, -2, -1, 0, 1, 2. So it shows the orientation. And then as you can see for our d orbitals, or sorry, our f orbitals, you can have all the way from -3, -2, -1, 0, 1, 2, 3. And so those are the shapes. And we'll actually show later why these shapes are these shapes. We'll show the mathematical function that gives us these shapes and derive it by solving the Schrodinger equation. And we'll also use math and principles of quantum mechanics to derive the Pauli exclusion principle. So that's that will be very interesting as well. So even though this seems like a very non-mathematical statement that, right, you can't have 2 electrons have the same, you can't have any number of electrons, 2, 3, no 2 electrons, no 3 electrons, etc., can have the same set of quantum numbers. And we'll mathematically describe this principle and show why it is true. Okay, so now the last thing, we talked a little bit about the Pauli exclusion principle, and now we can compute how many electrons are allowed in each orbital. So each set, or not orbital, each subshell. So each of those overall shapes, right, with a value of N and a value of L, right, because that corresponds to the energy. How many electrons are allowed in a subshell? Number of electrons in a subshell. This is, again, you may want to note that these are the number allowed in the subshell. Well, this is, right, it's just double the amount of ML, because for each ML you can have 2 electrons. So this would be 2 times 2L plus 1, or 4L plus 2. Okay, so notice each of these, if I wanted to write how many number of electrons each of these could have, an s orbital could have 2 electrons. A p orbital And a p orbital can have 6 electrons, a d orbital can have 10, and a f orbital can have 14, a g orbital, hopefully you see the pattern, could have 18, etc., etc. And so that's the number of electrons that we can have in each orbital. You could also compute how many electrons are allowed in each value of n. And if you actually do that, what you'll get is it's 2n squared, and I'll see if you can figure that out on your own, but that's not super important. The very last thing that we'll talk about in this video is something called degeneracy. And degeneracy is just the number of quantum states, right? And the state is sort of just the set of quantum numbers, the number of sets of quantum numbers that all have the same energy, right? And what that means, because there's only one electron per set of quantum numbers, that's really how many electrons can have the same energy. And so the degeneracy, which will be a function of L, right? L is the quantum number that will determine how many electrons are allowed in that energy, right? Because each of these, we'll talk about more of that in the next video of how each of these have different energies. The degeneracy, I'll say d of L is equal to 4L plus 2. This is the degeneracy. This is the number of quantum states. A quantum state, again, is the set of quantum numbers that have the same energy. So if you have L equals 2, then you have 10 sets of quantum numbers that have the same energy, right? Because then you have 5 different ML values and then 2 MS values for each of those. So that's the degeneracy. The degeneracy, again, the number of quantum states that have the same energy. And it's a function, in this case, of the azimuthal quantum number that will tell you how many different quantum states there are with the same energy. So, and then combining that with the Pauli exclusion principle, it has the same meaning of how many electrons can have the same energy. And that will be an important concept for later. So I'll see you in the next video.